Let's talk about number 9. Number 9 is one of my favorites because it talks about making hoops. Shooting a basketball. A free throw or a foul shot that they use in this problem is going to be denoted as either a success or a failure. Now, the way that this problem is worded actually needs us to define a couple variables to make sense of what we're doing. If you see here, it says a basketball player made 80% of his foul shots during the season. Assuming the shots are independent, find the probability that in tonight's game he, part A, misses for the first time on his 5th attempt, he makes his first basket on the 4th shot, and he makes his first basket on the first 3 shots. If you notice the key words here, we're interested in the first time that this basketball player does something. Whenever we see the word first happen, that's a strong indicator that we will be using the geometric model. As a reminder, in the geometric model, we care about the first time that we actually do something. Now, in this case, if we look at the questions, we care about the first time that he misses, but we also care about the first time that he makes a basket. So, for this problem, I'm actually going to define 2 variables here. X will represent the probability. We need to define a few variables. In this instance, X will be the number of shots, or the number of trials, until he makes a basket. And we'll also define another variable, Y, which equals the number of shots, or the number of trials, until he misses. We need to define these 2 because the problem asks for the first time he misses and also the first time he makes it. Because of that, we can't actually use X for both of them, and you'll see why. For this problem, we're only going to do parts A and B, and hopefully you can figure out part C, which is a little bit trickier. We'll see that after 5 trials, if he misses it once on the 5th try, but he makes it the first 4 times, that will yield us a probability of about 0.08192. Part B asks us, find the probability that in tonight's game he makes the first basket on the 4th shot. In this case, we're not looking at Y anymore, because Y was the amount of times until he misses. X will be the amount of times, or the number of trials until he actually makes a basket. So in this case, we want him to make a basket on the 4th trial, on his 4th attempt. So the probability that this player makes a basket on his 4th attempt will need to equal to the probability of him not making the basket 3 times multiplied with the probability of him actually making the basket. In this case, we switched the P and the Q's because in the scenario where we used X, we care about him actually making it. In the other scenario, we care about him missing it. In this problem, once you go for a solution, you will find that the probability of him making a basket after 4 attempts is going to equal a value of 0.0064. This answer makes sense because if he has a shooting percentage of 80%, we expect him to make it. So if in this case he misses 3 times in a row, that's very unlikely, which is why it's a low percentage. For number 3, or for part C, you should really go out and try doing it yourself. It says, find the probability that in tonight's game he makes his first basket on one of his first 3 shots. Which means you are going to be looking for the probability that he makes his basket on the first shot, or, remember that or, it's coming back in here, there's the words and or. And is multiply, or is adding. The probability that he makes his basket on the first shot plus the probability that he makes his basket on the second shot plus the probability that he makes his basket on the third shot. Take a look at the solutions guide to see how they did it if you need a little bit extra help. Number 17 is the first problem that we have that actually combines together the binomial model and the geometric model. For you lefties out there, this problem's for you because number 17 looks at the probability of somebody being a lefty. Now, the problem actually states, assume that 13% of people are left-handed. If we select 5 people at random, find the probability of each outcome described below. So, I'm going to put here the probability of a lefty equals to 13%. In addition, we are running n equals 5 trials. So the problem starts off by stating the probability of somebody being a lefty and tells us the number of trials we have. Now, in order for us to make the most sense of whether or not to use the geometric or the binomial distribution, we need to define a couple variables for us in order to think of a problem a specific way. In this case, we'll be identifying the variable x. I'm going to say the words, let x equal something specific in terms of, let's say, a geometric model. X is going to be the number of people checked until we get our first lefty. In this case, x is going to help us define our geometric model. Keyword here, first. In addition, we're going to let another variable, y, equal the number of lefties within 5 trials. Or in this case, within n trials. We're looking for the number of successes in this case, the number of lefties within 5 trials. Here, when we want to look for the number of left-handed people within a certain amount of trials, we're actually defining conditions for a binomial model or a binomial distribution. Find the probability that the first lefty is in the 5th person we choose. Once again, if we care about the first lefty, we're talking about the geometric model. So for part A, where it says first lefty, the very first lefty is the 5th person. We're going to be using the geometric model. We're going to use the geometric model because there's a keyword here, first. So, let us find the probability that the number of people checked until we get our first lefty, let's say the number of people is going to equal to 5, the 5th person, until we get our first lefty. So let the probability that there are 5 people until we get our first lefty. In this case, we're going to have the probability of somebody not being lefty, which in this case is 1 minus 13%, which is up here. The probability of somebody not being lefty is going to happen 4 times, multiplied by the probability that somebody is a lefty. To define this further, this is not lefty, multiplied by the chance of us becoming a lefty. In this case, if you do the math on your calculator, we get that the probability of us finding a left-handed first person on the 5th attempt is actually going to be 0.0745. Once again, if we're looking for the first lefty after on the fifth person, that means the first 4 people must not be left-handed. The fifth person has to be left-handed. So we need 4 times for somebody not to be lefty after we choose them, and then the 5th time have them actually become a left-handed person, or be a left-handed person. Part B changes the game a little bit, because Part B discusses the probability that there are just some lefties within the 5 people chosen. So this is the probability that there are just some lefties within, I'm going to put n equals 5 people. The problem stated that we have 5 trials. In the 5 trials, we just want to know if there's some lefties. Whenever you see this word, or this phrase, some, you can have 1 lefty, or 2 lefties, or 3 lefties, or 4 lefties, or 5 lefties. Now, you can find the binomial probability of all of those and then add them up. Or we can actually discover what's the probability of having 0 lefties and just taking the opposite of that. Because we want to make sure that there's some. The only opposite is that there's none. So what this would look like, 1 minus the probability of y, because y is the number of lefties, so we're looking at the probability of the number of lefties equal to 0. Now the problem wanted us to have some lefties. The opposite of some lefties is no lefties. So if we find the probability that there are exactly no lefties within those 5 people that we chose, we can take the opposite to show that there's actually at least 1. In order to perform the math on this, we need to focus on this piece first. So I'm going to rewrite this and allow us to look at it. I'm going to do 1 minus the probability of y equals to 0, and remind us that we're actually finding 1 minus n choose x, but in this case we're going to use y because y is our variable of interest, multiplied with our probability of us having a lefty, which is 13%, raised to the 0 power, because I don't want that happening in this case, multiplied with us not getting a lefty, which is 1 minus 0.13, 5 times. In this problem, we're looking at not having any lefties because we want to find the opposite. Instead of doing this same operation 5 different times, it's easier for us just to do it 1 time to find a solution. In addition, if we replace these values here for this specific piece of the equation, we get n is 5 trials and y equals to 0. Out of the 5 people that we have that are chosen, we want 0 of them to be lefties. If you go back and take a look at the video right before this, you'll see how you can set up this piece of the equation in order to solve for it. When you do that, we will end up with 1 minus 1, because there's only one way that you can really have 0 people, or 0 lefties, multiplied with 1, anything raised to the 0th power is 1, multiplied with 1 minus 13% to the 5th power.